Plotting data using Desmos. Desmos is a free online graphing calculator that is robust, easy to use, and considerably simpler than Excel. Also, it's free. You can use it for data analysis in this course. To get started, you can use any modern web browser to visit the site https://www.desmos.com/calculator to get started. There'll be a link for that on the course site, and of course you can just go to, say, Google and type Desmos calculator, you'll get to the same place. In Desmos, you can sign in using a Google account, and if you have one available, I would recommend doing it because then you can save your graph and look for other graphs. When you open up Desmos, you get the screen shown here where we have the title if there's a title. This is our action button. All of our equations and data and so on will live on lines over here, and then our live graph will live over here on the right. So we're going to use the add button to add items. For instance, we will add note text, which looks like this. And I suggest your first line should always sort of be just your name, because when you submit this, if you end up submitting it, it doesn't always come in with identifiers. This is really optional, but I think it's a good idea. Likewise, I think for your own use, you should probably put in a line that gives us the thing you're trying to graph, where it's coming from. So for us, we'll say this is lab 1, plotting data. Both of those are optional. They don't do anything. They just sit there as notes. As you get more complicated with Desmos, you can leave notes for yourself or for others if you're going to share your graph. But you'll see we added a note, and it doesn't do anything. Normally, Desmos will take what you type and try and make it look mathy and interpret it like an equation. These are telling Desmos, don't do that. This is not an equation. It's just text. For our purposes, we're going to want to be able to present data. So we should go and add a table. And we get, well, a table. Desmos doesn't know anything about what we're trying to do, so it says it defaults to sort of that math default of x and y. And it puts the 1 and 2 in case, or the ones here in case we have other data sets and we'd have like an x2 and a y2 and so on. But we do know what we want to do, so we're going to turn these into meaningful names. We're going to be plotting the circumference as a function of the diameter of a circle. So I'm going to call, instead of x1, I'm going to call the horizontal variable just d, and I get there by selecting that header and just clicking on it. And likewise, I'm going to call this just c, and now my table reflects my data, which will be useful later on for us to manipulate it. It's optional. You can call the variables anything you want, but your life will probably be happier if you try and make the data tables reflect the actual quantities that you're measuring. After that, we want to just enter data into this, and we can do that just by typing numbers and using tab to move over. So I'm going to reproduce the table from the lab handout, and I'm going to put these in here. And you can get your data in there from a bunch of different places. You can actually cut and paste it from an Excel sheet. So if you have a lab partner who's written their data down in Excel and they send it to you, you could pull it over. There are a couple other options, but generally you're either going to type it in or pull it in from so-called CSV data or from Excel. So notice that as we did this, Desmos was trying to plot, in fact, did plot the data. It defaults to a not great thing. It just sort of has the, again, math industry standard of -10 to 10 on both axes. Our data doesn't really fit there, so we're going to have to adjust the scale ourselves. This is a place where sometimes Excel does a little bit better because Excel will automatically scale, although in my experience, it has kind of a weird idea of where things should be. So we're just going to do it explicitly. We're going to go and say, let's make our data what it should be. And we're going to do that by going through the settings menu, which is this little wrench over here, and we click on that and get a new box. There's lots of things we can change. What we're going to change right now is where the x-axis goes. I'm going to go from -1 to 8, and I pick those values so as to encompass all of our horizontal variables. And then I'm going to take the vertical variable from -3 to 25 so as to encapsulate all of our data on the vertical axis. Also, you get to label things for the axes, so I'm going to call the horizontal the diameter d, and I'm going to say it's measured in meters, and I'm going to call the vertical the circumference c, also measured in meters. Desmos doesn't actually know or care about the units on the axis. It's not sensitive to that, so you have to sort of keep track of that, but it's certainly good form to make sure you put it there. And then we basically have this, which I think for this lab project will be all we'll need to do. You can do other things. You can turn on the graph, turn off the graph. You can put arrows in the graph. You can use this button to zoom to a square, which is nice, where it basically finds the best that fits your range of data. So if you enter in X values, it will find the Y value that sort of squares out the region, makes it look pretty. I'm not going to do that because we've already picked them explicitly. When we're done, we then click on this, and we can see that we have much nicer representation data. All of our data is on the screen now. As an aside, how did I pick those values? Well, I wanted to have the axes here, which as you know are at sort of diameter of 0 is this line, and circumference of 0 is this line. And if I had just gone from 1 to 7, then I would not get the axes. They wouldn't show up. Just technically they wouldn't be rendered. So I wanted to force them to be rendered so I can get them on my graph. This is kind of vanity. It just looks better for me, I think. And so my general rule of thumb is to go to sort of whatever the maximum positive value is, to go to minus 10% of that value. Since our maximum value is sort of about 10, I went to minus 1. And likewise, since our maximum value here is sort of about 30, a little bit less, then I went to minus 3. Where you go is up to you. You can adjust it all you want to make it look like you want it to look. But that rule of thumb has, for me, traditionally worked out pretty well. As an aside, Desmos does not let you assign sort of a title to the graph. This is another feature Excel has, which is sort of nice because it gets all wrapped into one place. Desmos doesn't let you put stuff on the page. There are tricks to get around that, but they're kind of annoying. So sadly, it doesn't have that feature. From our context, that's fine because you're almost never going to actually print out and hand in the Desmos graph. You're probably going to cut and paste this into another document like from Word or Google Doc, whatever, where your lab report is going to be. So it's fine that you can just put the title around the pasted image later. And they'll probably be, it's pretty easy. All right, so far we've got a nice looking graph, and pretty pictures make people happy, but really the purpose of this is to do stuff with it. It's to so-called fit the data. We want to find an algebraic relationship among these quantities that allows us to understand how they're related and maybe predict things from where they come from. Usually, because experiments are noisy, the data won't actually obey an exact representation. Even though maybe in sort of theoretical world it would be. If you really measure stuff, it would be very unusual for it to follow precisely an equation. Instead, we do what's called a fit. We fit to the data, and we say, we think it looks like this equation. What's the closest we can get that equation to our data by playing around with numbers, what we call fit parameters. So it turns out fitting is a well-defined mathematical process and depends on advanced statistics and even differential calculus, and it isn't particularly fun. But luckily, it's also really easy to program, and Desmos, like Excel or really almost any mathematical package, has been coded to perform these for you. Unlike Excel, this is where Desmos really shines. It's really intuitive to get this going, to figure out the fit that you should use. So we're going to take our graph, and we're going to say, that kind of looks like a line. It looks like all of those data points might fit on the same line, and we'd like to find the equation of that line to connect to the circumference of the diameter. And if you remember from geography, the answer is not going to be particularly shocking, but we'll see what falls out. In analytic geometry, two quantities x and y are related by a line if they obey an equation of the form y equals mx plus b. Maybe you remember this from Algebra 1, where m and b are some constants. M is what's called the slope, mb is what's called the intercept. Our variables are not x and y, they're d and c, but the idea will be the same. One last little Desmos tidbit, little weird thing. We're not actually asserting an equality. We're saying we'd like to find the m and b that best represent this line. So Desmos doesn't let us use the equal operator. Instead, we have to use the tilde operator. Not a big deal. So we're going to tell Desmos that we want to fit this equation, and so in this line we can actually type the model we have. We're going to say we want the circumference. We use the tilde to represent that we're modeling it rather than asserting an equation. And then we're going to say we want it to be m times d plus b. So we want it to look like an equation, but again, we've replaced the equals with this tilde to say, no, find the values of m and b that make it work the best. We get a bunch of things that come out then in that data line. We see under statistics a thing called r squared. R squared tells you how close your collection of data looks to the model that you're putting up. The optimal value is 1. The definition is kind of technical and weird, and it's very much a rule of thumb rather than a thing you should swear by. But r squared equals 1 means that our model passes all the way through all of our data points. This is because, as mentioned earlier, we faked the data. It's not real-world data. It was constructed. But you'll want your r squares to be sort of in the range around 1, hopefully more than about 0.8. Not to obsess over, but as a guideline. And then we also get these things called parameters. The fit parameters are the values of the constants that give us the line that best passes through our data. There are an infinite number of lines we could draw, but this one minimizes the average distance between the data and the model. Again, because r squared is 1, it actually exactly matches the data. That won't happen very often for you, probably really never. M is the slope from way back in Algebra 1. It's how fast the circumference changes as we change the diameter. And B is the intercept, which is essentially, in this case, what is the circumference when the diameter is 0? And we're not shocked that the intercept is 0. And we're not shocked either, really, from this value of M. So here we find that the value with a slope of about 3.14 passes through the data best. All right, that's slope we want. This is really not too surprising because the ratio of circumference to diameter, which is what the slope basically means, how much does the circumference change as we change the diameter, the ratio is known from geometry. It's actually defined as the number pi, and we know that the 2 decimal place value of pi is 3.14. In school, you might have heard it as like 3.14159, so on, so on. Pi is a weird and strange number, but it's approximately 3.14, so we expect that the circumference of any circle should be 3.14 times the diameter, at least within 2 decimal places. And again, with real data, we'd have had a different value there. We'd get some approximation, which would help us get what pi was. Really, historically, way back when, the first measurements of the value of pi were almost exactly like this, although they didn't have statistics or calculus at the time. But the idea was to draw lots of circles and figure out how the circumference was changing. And so the original value of 3 for pi was found from basically from that. All right, so our graph is essentially done. If we were looking for our value of m, if we were trying to just answer a question, this answers it right here. But if you want to talk to people, and half of science is communication of results, we'll want to move this graph to an actual place, a lab report or some other sort of document. It's relatively easy to do. We go over here and there's a button which is for sharing, and we click share the graph. It takes maybe 10 seconds for it to come up. It gives us a bunch of options. We can do a bunch of things. We can print directly. I actually have very little experience doing that. I don't find that particularly useful, but I guess if you just wanted to get your graph out on paper, you could do that. You can embed it into a web page. It gives you the HTML code that would let it live on your blog or Twitter feed if you were excited to show off your graph. You can copy this link, which is a URL, standard URL, and share that with anyone you want, and when they clicked on it, Desmos would make a copy of this graph for them to play with. So that's a way to do it. And there might be times when the way you'll submit your work is to actually write all of your lab reports sort of up in this space and then just submit the link to me through the online management system. But most of the time what you're going to want to do is export the image, which is this middle guy. And when you export the image, it gives you a nice little demo box, and it says, here you go, here's what I'm going to put out, this computer talking to us. We can play around with its size and we play around with thickness. I like medium square. You can do whatever is aesthetically to you. It really renders how big is the box and really how big is the scale that it draws. If we go small scale, we get a small box with huge scale marks because the box is small. If we go to a large square, we get a much more finely divided graph. Again, the compromise, not to be all Goldilocks, but the compromise seems to work pretty well at medium square. I also generally like medium thickness, which makes all the lines and stuff stand out some, so when they get printed or put on the screen, they're okay. But you can also go to thick. You can just see it starts getting in the way. There isn't as much distinction between axes and so on. And again, I don't care that much, but I like medium. And you can choose the one that you think is most aesthetic, and that's perfectly fine. Then you got to do something with it. So usually you could right-click on it in whatever computer system you use, and you can either open another tab and look at it close up, or you can save it, or you can copy it. And most of the time you could just copy this and then go to a Word document or go to Google Docs and just hit paste, and the picture will show up wherever you are in your document. And that's certainly the easiest and maybe most intuitive way to do it. The other thing you can do is download the PNG file, store it somewhere on your local computer, and then import it into your documentation program, whichever way you want. So in both Word and Google Docs, there are things that say insert picture, and you would just pull that file back. But either way, you would be able to get it pretty easy. At that point, it becomes a picture in your document file, and then you can do whatever manipulation to it, or put a title under it, or whatever you need to do, based on that it's now just a picture. That, of course, is no longer live, so if you change anything in the Desmos file, you're not going to change your graph. You'd have to